Okay, hello. We'll have a session on session types. This is part of my work at IOHK. We're working there on a cryptocurrency, you probably know. And we're writing protocols that will run this cryptocurrency. We're working on the next release. And we work together with guys from Well-Typed, with Duncan Kutz and Alexander Wies. And early this year, we were working on this session type framework, and they came up with a really nice solution for describing sessions in a typed way. And I'll be speaking on this. Our work on this framework. We're also being helped by predictable network solutions for working on the networking stuff like TCP and various things around that. So this workshop will be divided in 3 parts. In the first part, I will give you an introduction to this framework, which is very similar to the streaming libraries that you probably know of, like pipes or conduits or the streaming library. The second part will be a small presentation of a very simple streaming protocol, and the third part will be you will try to extend it and extend this protocol that I flashed, like a very beginning version, and you'll be able to work with this framework, add some additional features to it, and possibly add some pipelining. Okay, so let's get started. Actually, yesterday I was speaking with Edward Kmet, and he told this story that when he was working on session types at some point, and the pipes library that we have in Haskell was heavily inspired by his ideas on session types. So this thing is actually very similar to the ideas he had very early on. Okay, so in a streaming library, like here is a data type that describes a stream in the streaming library, and it sure. The comments are not important. Really, the definition here is important. That you have this effect type that allows you to include some effects in your stream in every step, and then you have here in this library you have this functor f that allows you to encode each step. And each step will be either getting a value or waiting for a value. And something like that is usually a functor. So, and a return type. Something slightly more general is in conduit library, which I have it here. This pipe type. So you have this need input thing that takes a lambda that is awaiting for an input, and you have something that presents an output, so is this O here that presents an output, so gives a value. And you have this effect thing that you can, this pipe M allows you to do effects inside this pipe type. And something also similar is in the pipes library. There is this type proxy, maybe slightly bigger. Here it's slightly more general because it allows to speak both ways, to upstream and downstream. So the request can give a value and await for a value, and the same for the respond. But if you forget about A prime and this part, you have something like request a value and respond with a value. And then you have the same trick to embed monadic computations to in the proxy type. So you can do some I/O thing in between of awaiting or producing values.
So what is session types here?
And one second. Yeah, that's the next step. So there's no session here, so there's no session type. But the important part for writing a communication between two parts, they might be two servers, but they might also be just two threads in your computation, is that one will either await for a value or will produce a value or do some monadic computation. And this is what those three libraries do. They allow you to produce some values or wait for some values or do some monadic computations. But in a session type framework, you would like to have a matching kind of dual session that if this side produces a value, the other side will consume it. And whenever the other will consume it, the other will await for it. So, and this is the session type thing that we'll introduce in the next thing. So one way to model it is to add agency to this streaming thing. Like say, who's the agent of a given on a given step? So who's responsible for producing the next value? And then encoding that on a type level so that you can only produce, when you produce typed matching descriptions of your two sides of your protocol or your application. Okay, so the main type in our library is this. Maybe it should be bigger. Yes?
Is it always regarding bidirectional communication? You're not taking into consideration publish subscriber communications? Because you're saying
yes,
always someone producing a value, there is always one consuming this value.
Yes, it's one-to-one.
Okay.
It's one-to-one. But you could implement a subscriber and with like Unix socket, and just every communication will be done using this protocol that will speak the given session type.
Can we have it even larger?
Sure. Okay, so the peer type is the type that will describe this stream of values, and it has various type parameters. This first one, PS, is just a tag for your protocol, which you might want to have different protocols, so this will make them different. Then there is this p-role kind, which has just two values, which means two types, because it's a lifted type. Either it's as a client or as a server. So this means that you might only have two peers for a given protocol, one side or the other. We called one client and the other server. But actually, the names do not matter. Just you need to have just two, and that's all that matters. Then this st of this type st of kind ps, which is this protocol thing, will describe all the states of your protocol. And in a given state, both sides have it. So if you have a client and a server, they might be in some given state. And what this framework will ensure that in a given state, only one of them, either the client or the server, will produce the value, and the other must be dual to it, so must listen await for that value.
Another question.
Sure.
What extension allows us to annotate with kinds so that we have types that we expect?
So for this, you need data kinds that you can promote types to kinds and terms to types. And you probably need, like in this model, you'll need slide.
General ADT.
Also JDTs, right?
Yeah, sure.
General
JDTs, polykines, and various other. Actually, not that much. Polykines and data kinds are the most important ones. Type families are in this presentation, but there could be done a different presentation without type families. And the most important part actually are the GADTs, and the presentation here is heavily using them. Okay, so.
One question.
Sure.
There is protocol type identifier and protocol state. So there is a functional dependency between these, right? In the peer type, right? Yeah, so you have PS parameter, which is protocol kind of type value. And then you use this PS in ST.
Yeah, which means that PS is a kind,
Right.
and ST are all the types that this kind provides.
So why do we use PS? Because we can just take it as a kind, right?
Yes.
We don't need the first parameter, right? Or do we?
You might need it.
Might need for the effect. Otherwise, it would be a way to depend on PS in the definition of effect.
You might need it, but this is
PS, PR, ST, right?
it's still there, but this is a technicality that we can skip. Okay, so how you can construct the peers? So one thing that you have is really the same as in the streaming libraries, that you can have. You can compute these peers using a monadic computations, which allows you to embed I/O actions in between the calls, in between this peer. So if you are waiting for something, you might do some I/O, or when you received something, you might want to preserve it in a database. So that's why you often need this effect thing. Then is the done constructor, which allows you to finish the protocol, and it takes 2 arguments here instead of 1. One is the value that you want to finish your protocol with, and another one is a singleton, which gives a map between this, which gives access to this state thing, because state, this st, is of kind, has kind, this st is of kind ps. So this st is a promoted thing. So it doesn't have any terms. It doesn't live on a term level. It's a type without any constructors. So the only access you can have to it is by constructing JDTs, which will give you this access to it. And these are singletons, and this nobody has agency is a singleton for this st. There will be 2 more such singletons, and they're actually useful only when you are dealing with it's like trying to write a codec for your protocol communication, where you want to have access to the state. You want to know that your protocol is in a given state. You want to pattern match on a state. That's how singletons are. How singletons are very useful. There are only 2 more constructors. One is yield, which allows you to yield some value. So this first thing is again a singleton that gives you access to this state thing, but it also has this parameter PR, which is the kind, peer kind, which is either client or a server, because the server will do something different from the client in a given state. Message type, which is literally the message you will be sending on a channel. So this is the real protocol message that you will send through your socket or whatever. And this message is a transition also in your system, in your state diagram, from the state st to st prime. And this way you can encode state transitions by these messages. So this messages gives you all the graph of state transitions. And since we're constructing a peer that is given in this state, and we're giving in transition from state st to st prime, the continuation must start in this type st prime. So this is the continuation, and this is the current transition, and the state we're in.
Why does it go backwards?
It goes forwards.
Okay, so
This is the state we are in.
This is JDT syntax, so just reverse a bit.
This is the transition from what we are in right now to the next state. And then you give what will happen after the transition happens.
oh, right, JDT syntax, right.
Yeah, and this is JDT syntax, so it's just a record of things, actually. And these arrows are just a syntactic sugar to have some nice notation for it. Okay, so this is how you produce values, produce messages. So if you have an HTTP server that gives responses, this would be this response here. And another thing that we want to be able to do is to await for things. When somebody is sending a value to us, we want to wait for it and do something with that. And the usual trick is to just give a function that consumes the message and gives the continuation as an output. And again, here we have we construct something in a state st, and whenever it receives something, some message that transforms the state from st to st prime, we need to get a continuation that starts in this state st prime. And this they have agency is a singleton that says it's not me that I have an agency, it's the other side that has it. So they're responsible for sending messages. And as in the other, as in the yield case, it has access to this peer role and state. There is also associated class which defines this these gadgets like message, agency, stuff. There is this protocol type class that, so you want to define your protocol PS, which is a promoted data type, so it's a kind, which types described all the states in your state transition system, in your state graph. And to give an instance, you need to define various things. You need to define all the messages that are allowed in your state machine. So which you have all the states, and you want to connect some of them with some transitions, so like arrows. And this will be the messages, like in a simple ping-pong protocol, you would have two messages. One would be ping, and another would be a response pong. And we'll see an example like that shortly. And then you need to define this client has agency, singleton, server has agency, singleton, which were used in this peer constructor. And so these are simple GADTs that says, that gives some tokens on which you can pattern match to give access to this promoted type ST.
One question.
Sure.
How do you assure that only client has agency or server has agency, so that they are mutually exclusive?
That's below the screen. So there are few lemmas that you need to provide for this type class to be fully correct. And this is exactly it answers the question how we ensure that it's only client, only one side that has the agency. So we have three lemmas, and all of them have this form. If you you should be able to define this function that if nobody has an agency and client has agency, that you must be able to produce a void, which means a contradiction. So it should not be possible to define such a function. And Haskell has a very nice extension to defining functions like that, with empty case, using empty case expressions. And it can infer that you defined it correctly. And another two lemmas that you need to provide is that if the system is in nobody has agency state and the server is an agent, then it's also a contradiction. And
the first one, because there is.
One second, where's the first one? Yeah, and the first one. If a client is an agent and the server is an agent, then it's a contradiction. In Haskell, you could define those functions as undefined and be happy with that. But that can be easily rejected in tests where you get an error if you do that. So. Okay, let's do a simple example. Okay, so this is a ping-pong protocol, very simple. You have three states in the state diagram. Is either the system is in the idle state or in the busy state, or we're done, and no communication will be done anymore. And this is this promoted data type, so we will use this ping pong as a kind, and state idle, state busy, and state done will use as types. So they are purely type level things. And the protocol instance for this ping pong thing will have three state transitions. You have a ping message, pong message, and message that we're done. And the ping message is a transition from idle to busy. So if we are a client and we send a ping message, the system becomes in the busy state. Then we have a message pong, which is a transition from busy to idle. And we have a message done, which is a transition from the idle to done state. And if we wouldn't have this machinery which describes this singletons things, we wouldn't have additional information that we need. We need to have an information who is the agent in the given state. Because we could give erroneous definitions, like defining that the client is agent in all those states. But it's not the way ping pong does, because in the ping pong, the client is the agent first. It sends the message to the server. The server becomes the agent and replies with a pong message. And at this state, the client can choose and send idle ping or done. So either ping backs and receives a ping, or it says we're done and we're finished. So this is this very simple types client has agency are defined for saying who's the agent in a given state. So here we say that in the idle state, the client has the agency. In the busy state, it's the server that has the agency. And in the done state, nobody has agency, and no message will be exchanged. And then you can define these three lemmas in a very simple way. You just pattern match on it's a client and the server has agency, so the stock idle is has this type, client has agency. And this other tag, singleton, Haskell can infer that there is no constructor that can satisfy it. And if you use empty case extension, it will happily agree on that. And the same in the other two cases. If nobody has an agency, there is no state that you could fit in here. Because only way to break it would be to add a constructor here. For example, add a constructor here that would say that this add a state here, and then you could match something here, and you would be forced to produce a void value, which you cannot. So that is how your okay, maybe a simple presentation would be a nice thing to go forward. Or any question? Yeah.
How related is that to battery networks?
This is a slightly different approach, much simpler, because it's what you have here is a graph of states, and this is this message thing. It describes you all the transitions in your system, and the peer describes you all the possible paths in this graph.
So my question is basically because the agency thing is kind of like the dot in the battery network.
Yeah.
See this agency as related to message. So after the peer receives a message, it changes
It depends on the protocol. It depends on how you define a protocol. It can be like that you send a message, and together with that message, the agency changes. But it can also be like that, and we will see a protocol like that you send messages, and the agency stays with you. You're just expected to send more. So like if you're streaming something, like streaming a video in small chunks, you would like to do that you still are the agent, and you just give all the chunks, and when your stream finishes, you will send a final message that will give the agency to the other side.
So my question is, why is this information about agency is not part of the message?
In a way, it is, because it's where is the So, for example, here you have this transition from this state to the other one. And you know that in this state, who's the agent in a given state. It's predefined by the protocol. So that part can be actually inferred by Haskell, but by the type system.
This value, you don't want to have this information.
You don't need it because it would be redundant because it's already.
I was thinking that you have this information only in the message.
No, it's assigned to the state.
You just send in the message.
But how would you describe correctness condition? Because here correctness condition is from that for each state you know who is going to send message first, and here you could send different messages, reach the same state, and you wouldn't know where to go.
Yeah, it's statically you know who's the agent in all the states, and this way you can have static property of this protocol that you will never have two parts listening to each other and awaiting for a message.
Okay, this makes you in this situation it's difficult to write this lemma you mentioned.
Yeah.
You don't have this,
Yeah.
So a question, yes. So, is there not a danger if you rely on static compile time guarantees for your client for the network protocols that you become oblivious to the fact that someone else could write their own client which doesn't have set guarantees, it still sends messages to the server when it's in the wrong state?
You will actually notice that somebody is violating your protocol, and in this case, you want to error. You want to shut down communication with that party because it's not following the rules. So if you agree on the rules, and these rules actually can be written in a very simple way as a state diagram without this type level information. It directly translates to a simple diagram that is very easy to re-implement without static information.
Okay, so the logic can be regardless. Yeah, I guess I'm getting confused between the validation on the client and the server side. I guess if it's the protocol level, it's both.
Yeah, like in this example, if you're the client and you want to send a ping message and you instead of no, this may be something different. If you're the server and you're awaiting for either ping or done message, and somehow the client sends to you a pong message, what can you do? You can only shut down the connection because you don't have rules to follow the protocol. So this gives you you will early on discover when somebody is breaking your communication protocol. And if you're developing an application, that is very useful to actually know that, oh, I broke a rule here, and you can fix it early. And have it done right on the. Okay, so everything actually lives in a package that is available on GitHub, and we have a small demo for this ping pong protocol. I just need to check where it's. Okay, demo chain sync. So what this demo will do, it will run this ping pong protocol over a Unix socket. It just needs to compile. Okay. Okay, this is the running server, and in another session, we'll run the client. Cabal new run demo chain. I think it's that. Ping pong. Okay, so what happened here is that the client, which is here, send a ping message, and it received a pong message. Send another ping message, received another pong message, and after I think 5 or something of those, send a message done. And here we'll have a dual thing. So the server received a ping message and sent a pong message for every ping, and at the end received message done. So this is a very simple protocol, but what's missing in this thing is that when you define this protocol this way, you lose lots of time, because when you send a message, for example, here the client might know that it wants to send 5 pings, and it will happen like this: that it sends a ping, waits for the response. So it's 1 round trip time, and then sends another ping. It has to wait for another round trip time, and do this 5 times. So you do this exchange of 5 ping pongs in 5 round trip times between the client and the server. If your client is on a different continent than your server, you will lose. It will take like about a second, because it takes probably like 200 milliseconds to send a message from a data center in US to Europe. So that's not really ideal. And one really nice solution for that is called protocol pipelining. And if you type in Wikipedia, yeah.
Should I be getting multiplexer errors when running this code?
No. You might. Yes, you might. Yeah. Yeah. because there's additional layer that we're not speaking here about, but yeah, you discovered it. So protocol pipelining is designed to do this latency hiding in this way that, so we've seen this way of communicating, that you send a ping, you await for the pong, then you send a ping and you await for pong. And ideally you could do actually this, that you send 3 pings messages and then wait for the arriving pong messages. And this transformation from no pipelining to pipelining does nothing to your state transitions in your diagram. Your system will follow the same state transitions. They will be only timed differently.
So is it the case that when I send 3 ping messages, it's as if there were 3 instances of me and each of them is going to transition to the next state independently? No,
they do that sequentially, because you send the messages sequentially in a sequence. But since you know that you send 3 ping messages,
I await 3 responses, and only after that I transition to the next state.
Yes, you know what to expect. And
This implies that you really don't process any information from this other party. Because if you must wait for receiving message to send another message, if you depend on the data.
on exact data, maybe you don't depend, and then you can do this pipelining thing. Like when you're streaming a video, you don't really depend on a TCP level. You might depend because you want to resend something that didn't arrive, but on a application level, you don't depend on a previous messages that your chunks went through, because you assume you have reliable channel. So you're just streaming them and you're not waiting for the confirmations.
Wasn't your ping message defined as a state transition from idle to busy?
Yes.
So how can you do 2 ping messages after each other? Because when you do the first one, you're in state busy. In state busy, you can only do receive pong, right?
But you know that you will receive a pong, and you're back in the...
Calculate on the future that you will receive it?
Well, in this case, that's the only case possible.
Or you can receive done.
No, you only can send done.
You can only send them.
You can only receive pongs. So in this diagram, you can do that. It's not that every protocol, you can pipeline every protocol. There are multiple protocols that you cannot pipeline, like the server side of the ping pong protocol. You cannot pipeline pongs messages because you don't know what you will receive. And this is your case, that you don't know if you will receive the ping or done.
You can receive 2 different ones, but the client can only receive 1.
Yeah,
That's why you do this.
yeah. But whenever you can do that, it would be really nice to be able to encode it in this way, so you can have really nice streaming done in your protocol. Okay, that's the first part, which describes the protocol. On the next one, we'll be doing a streaming protocol, so which is very simple, and then if we'll have enough time, do some pipelining with it. And the prerequisite for that is to clone a repository that I prepared. Is this Monadic Party 2019 thing on my GitHub. And you can compile it with Cabal new build. And yeah, that's it. And there's another requirement that it.
Can you zoom in because it's
Sure.
visible which kind of introduction.
Discord.
Yeah, I posted on Discord.